clearly audible to me. Very nice. A very good morning to you all. In the three-phase AC circuit subject, in the previous class, we just took ourselves how is that generation of three-phase AC takes place, how that rotating field mechanism induce an EMF in all the three windings symmetrically and balanced mode as EM or Vm sin omega t, Vm sin omega t minus 120 and Vm sin omega t minus 240. And the running cursors on the wave show you how that individual phase waves are drawn. And another is shown in the right side top corner, how three phase waves are drawn on the scale. Then the three windings which you will see on the animated view, red colored and blue colored, green colored, you will see the windings representation. So those were drawn as a windings here as a B, C set. These three windings are having 6 terminals. Start of the winding, end of the winding, like that. Each winding will have start and end, like that 6 terminals are there. By suitable interconnection of those 6 terminal one to one, one to another, I have to create optimal connection. Then I should prove that two different voltages are possible in three-phase AC. In that perspective, interconnection of three-phase system work as star connection and delta connection. What is star connection? How it is formed? What is delta connection? How it is created? We need to understand. Once we understand what is that relationship exists between line voltage and phase voltage, line current and phase current, that we need to understand. In line with that, let us take a view of three-phase AC generator. We also call it a synchronous generator having 3 windings, 6 terminals. Those 6 terminals are suitably interconnected to create the one which I am showing with the cursor, a star. We will find finally how many? 1, 2, 3 and a common point, only 4. Out of the total 6 possible terminal, only 4 terminals are brought out of the machine. We call this as 3-phase 4-wire system. That is also known as star connection system or Y connected system. The other is 3-phase 3-wire system, which is delta connected. You can see same 3 windings are end to end. The finish of the first group connected to the start of the next one. Finish of the second group to the start of the next. Finish of the last group to the start of the first. Cyclically connect them, make them order. Then from the connection, you can see here start, end, start, end, start, end. This way they are connected one to one, one to one. Voltages are brought out as 3 terminals. You will find 3 terminals only. So this is called 3-phase 3-wire system. This do not make any change in our Vm sin omega t, Vm sin omega t minus 120, Vm sin omega t minus 240. These things will not get affected if I connect in star, if I connect in delta. What matter to us is once there is an induction of EMF by this way, by 3 waves having 120 degree apart each other. Suppose the connection of the generator is said to be star, I can read 2 different voltages as voltage between line 1 and line 2, line 2 to 3 or 3 to 1. Between the lines when I measure, that is we measure it as line to line voltage. The another is any one of the line with the common point. If I hold the meter and check, that is called phase voltage. So line voltage and phase voltages are not the same in case of star. But in case of delta connection, there is no common point generated. Therefore, any voltage I read between any 2 terminal is line voltage. It itself is the phase voltage of A. Between 2 and 3, when I read it, it is a line to line voltage. But it is the voltage of B phase. If I read the voltage between last and first terminal, it is no doubt a line to line voltage. But it is in turn voltage of a C group. So we find line voltage and phase voltage same in delta. That is what we want to know vectorially in the today's class. That would be one good question. Explain three-phase star connection and relate line and phase quantities. Explain delta interconnection of three-phase AC. Relate line and phase quantities with the aid of vector diagram. That would be a question. To have it dealt properly, let us start our understanding. Star connection of three-phase AC system is formed by suitable interconnection of the three-phase windings. I have picked the same image you can see. Three windings are such a way connected. Suppose if I consider A group. A group is having start, end. B is also having start, end. C is also having start and end. I have to make one common point. End of the A, end of the B, end of the C. I can twist and create a common point that you can see here in this diagram. Suppose R and R dash, Y and Y dash, B and B dash, like your A and A dash, B and B dash, C and C dash. If I call one of the common terminal dash, R dash, Y dash, B dash is joined, created a knot, brought it as a common. That's called common point. What about the remaining 3 points? R is left off, Y is left off, B is left off. Those you bring out it like this way. By this what you did? It looked like a star structure or a Y like a structure in which one common point of R group, Y group, B group is joined and created as a common point. Remaining left off points of R group, Y group, B group were brought out as it is. So such a connection look like a star and we call it as a star connection or Y connection. There is no difference between induced voltages. Induced voltages will remain the same. You can see the same wave I have reused here. But it look, this structure what I have shown at the left bottom will become in this way scientifically. There is a joint of end of A, end of B, end of C, call it as a neutral. The remaining end of A, B, C were brought out. So I have out of the total 6 terminal, only 4 are usable. So between any one line R and Y, you can see here R and Y, VLL, line to line voltage. Between R and B, you can see here line to line voltage. So between R and N, can you see this? V phase voltage, voltage read or voltage induced in R group. Similarly, Y and N, Y group voltage, B and N, phase voltage. I call it as 2 different voltages are possible to read in star connection. So therefore, we need to relate line voltage with phase voltage. Similarly, what about the currents? Suppose we learned what is the line current, what is the phase current. We learned in the earlier interaction. Any current entering the line or leaving the line, we called it as line current. Any current coming out of the phase group or getting into the phase, we called it as phase current. And we discussed very clearly. In case of star connection, suppose any current is going out of the winding, it has to go out, it has to come out like this way. Phase current and line currents are one and the same. So therefore, whether it is a B current, B group current is coming up, coming out as a B line current. While current in the phase Y is coming up, going out, or it is coming into like a motor. It comes from a line, it enters the phase. So currents are same in star connection. So how to relate it technically then? Just observe the another diagram drawn here. The same kind of work is being represented. Like A, B, C group which is mentioned, you can say A to N common point, B to N common point, C to N. The same structure is being, common point is drawn at the center. A, B, C are the left off point brought out of the external connection. Then you can mark the terminal description like any current entering the line A, IA, any current entering the B, IB, current entering the C, IC. So I mentioned the current. Then What is the voltage induced in the phase A? EAN. Phase voltage A with respect to neutral. EAN. What about the phase voltage in the second group? EBN. Induced voltage in B group with the neutral. What is the voltage induced in this third group? ECN. So what I am mentioning here, induced voltage in this V phase, what I am speaking in general, I am writing with respect to group 1, group 2, group 3 using ABC relation. EAN phase voltage of A, EBN phase voltage of B, ECN phase voltage of phase 3 or C. Now I mentioned line current and phase voltages. What about the phase current? If IA enter here, where it will enter? It will enter the phase current phase group here. It will enter to this. Therefore, line current and phase currents are one and the same. There is no distinction between I line and IPH. Both are one and the same. But voltages are not same. We will see one by one. When I say line current entering is the same phase current, line current entering here is the same current here, line current entering here is the same current here. You might wonder, sir, you are showing all the three currents are entering to a junction. Where do they will go? Yes, very good question if at all you are having in your mind. Look at the waveform here. This waveform, can you see? R group wave, correct? Y group wave, B group wave. We have three waves. On this graphical representation, let us imagine this is the current wave, like R group voltage, R group current, Y group voltage, Y group current, B group voltage, B group current. So they are also sinusoidal. They are also having 120-degree phase difference. Therefore, you will find according to KCL, when all the current enter here, what is that KCL? Algebraic sum of the current meeting at a point is 0. It means the waves which are shown, suppose these are current wave, the wave in the upper half of the graphical representation and lower half of the representation with respect to reference axis. X axis you call it a reference, minus, above is plus. Whichever the waves you find in the upper half are suppose getting into, the opposite is going out. You can see at this point you observe here, yellow wave, white wave are at this top. This junction I am considering. At the same time of observation, blue wave is negative. It means if there are currents entering to the junction by these two waves, the third wave is returning. At any moment of time, as I move from the graphical scale here, it is not that all the time currents are entering to a junction. Some of the currents entering to a junction, other is leaving. It may be one is entering, two are leaving. Two are entering, remaining is leaving. Like that, you can see it from, as you move from 0 mark towards the right side. The waves you find on the upper half are suppose driving into the neutral point. The wave at the same time is shown in the bottom of the representation is going out. Suppose you can see at this point, two are in negative plane, one is upper plane. What is the meaning of this one? White wave, suppose A group is driving the current into the junction. These two waves are driving it out. So KCL has to be valid. That's the reason. You need not worry about that. So IA is the current entering, line current and phase current are the same. IB is the line current and phase current is also same. IC is the current and phase current is also same. So that's what I need to convey you. Now coming to the other end of this. If I bring this A to the external world, B to the external world, C to the external world, I will have three lines or three terminals. Now, what is the line to line voltage? Line to line voltage is the voltage measured between any two terminals or lines. You can see here VAB I wrote here. I mean EAB. EAB means what? Red voltage between terminal A and B. I have to touch this A which is over here and touch B. Between these two leads, whatever is the voltage I am reading is called as EAB, because I mentioned A here, B here. Same thing you can see here. Line to line voltage means what? Line 1 open to you for the access, line 2 which is open to you for the access. Between these two, if you read the voltage, it is line to line. The same way EAB I am calling here. Suppose what is ECA? It is the between C and A. C is here, A is here. Between these two, whatever the voltage you measure, that is ECA, line to line voltage. The last one you can see between B and C, EBC. Now what I mentioned you all, I mentioned EAB, EBC, ECA as line to line voltages of a star connection. Now my question is, what is EAN? What is EBN? What is ECN? They are the phase voltages measured with respect to common point N. What are these EAB, EBC, ECA? These are the voltages measured between A and B, B and C, C and A without N. N is not touched here, only terminals are referred. Now my question is, star connection, explain star connection, relate the line and phase quantities with the help of vector diagram would be a question. Then this we need to understand as a representation. You got to know that EAB is not equal to EAN. EAB is not equal to EBN also, because these two windings are such a way interconnected. Between A and B it is EAB. It is not EAN plus EBN. We cannot add it because it's a impedance. This is a complex addition. You cannot do directly arithmetic. Therefore, you need to understand complex addition over here. So, we got to know terminal description, line to line voltage, line to phase, mean neutral, phase voltages, line current, phase currents in this diagram. Let us relate what is that value of EAB in terms of EAN and EBN. What is that ECA in terms of ECN and EAN? What is that EBC in terms of EBN and ECN? What is that I am trying to do? I am trying to bring a relationship between line voltage and phase voltages. For that, I have to draw vector diagram. What is that vector diagram? You can just see at the left corner of my presentation. So, I have drawn three vectors, 1, 2, 3. What are they? You can see EAN, vertically downward. Just observe this vector, correct? Then, here I have BN, here I have CN. These three vectors are the vectors of EAN, ECN, EBN, phase voltages of three-phase AC. What are the phase voltages? Voltages induced in the phase winding of the three-phase AC system. So, those are 120 apart each other. Therefore, I have drawn EAN, a vector downward, 120 behind are having a phase difference, EBN. Again 120 difference, ECN. I have three vectors space apart 120 each other, equal in magnitude because of symmetric system or a balanced system. So, I need to understand this Y-like structure, 1, 2, 3. These three vectors represent the phase voltages of a three-phase AC. That's the first observation. The second, we know that from the representation, right side I have a figure, line current and phase currents are same. Then I wrote it here. From the observation, in case of star connection, line current is equal to phase current. I can write IL equal to IPH. Then voltages are not same. EAB is not equal to EAN or BN. Then what is that? I have a relationship. I have a relation. Read here. From the vector diagram, I have to get relationship between EAB and EAN, EBN. How do I do it? We know that line voltage EAB. You can take any one. You need not take EAB, EBC, EC. Any one you take and prove it. So I pick EAB because already readily available on my screen. The line voltage EAB is equal to you can see here EAN plus ENB. It is vectorial addition of AN plus NB. If I add these voltages, that is nothing but EAB. Graphically, we can check this. So, EAN plus ENB equal to EAB. If I apply KVL in your mind, you can imagine. Therefore, EAN is phase voltage. ENB is opposite to BN. You can see it is ENB, not BN. Therefore, it is written as minus of EBN. So, NB and BN are opposite to each other. The vector you can see, the vector is towards, NB is away from that. Therefore, it is totally EAB is equal to EAN minus EBN. What I got finally now? Any voltage between any two lines like A and B, EAB is vectorial difference of phase voltage A with the phase voltage B, or it is the difference between the phase voltages of A and B. Then it is written as EAN vector. I have to find it is downward here, correct? Yes. Where is EBN? EBN is here, right side upward here, tangential. So minus EBN means reproduce that backward. Put it dotted backward. Can you see here? Then that is representing you EBN. Then take the vectorial addition of vector EAN with the vector reproduce backward BN. Then if I make these two vector resultant, I will be getting a point resultant like this, diagonal. Then on this diagonal, I have a small construction. What is that? The diagonal is the resultant voltage, which is nothing but EAB. I am in need of EAB only. To get EAB, I took vectorial difference of EAN and EBN. This is what I have done. Then that resulted me EAB. Then this diagonal bisect this angle. The angle between reproduced vector and the one which is vertically facing down. This total vector means angle is 60 degree. So this is 60 because other side I have 120 and this must be 60 plus 120 become 180 for a straight line. Therefore, this total 60 degree angular width is bisected by this diagonal. Bisect means 30 degree this side, 30 degree this side. So I get this angle as 30, first observation. Later, from the vertex of this A, drop a perpendicular to the resultant vector. Cut it at C. I got O, A, C and B at the end. I label them. So this become a right angle triangle here. This side is having an angle 30 degree. This is 90 degree. This must be 60 degree. Default, a triangle with the 180 degree side, 180 degree sum of the sides. Likewise, if I have 90 degree over here, when I drop a perpendicular, this is 30, this must be 60. Now my work is, I have got the resultant vector VEAB. Now I want to relate mathematically what is that relationship exists between phase voltage and line voltage. So for that what I will do, I will consider a triangle OAC, this triangle. You can consider triangle OAC. In this angle you consider. What is cos 30 of this? In this triangle, what is cos 30? Adjacent side divided by hypotenuse. Am I right? OC divided by OA. With that you can see here. Then what is OC in turn? It is OB divided by 2, because this is the total symmetric system. When I drop a perpendicular, this perpendicular bisect this diagonal. Therefore, OC is OB by 2 divided by OA. Now let us substitute. What is OB? EAB divided by 2. What is OA? OA is one of the phase voltage EAN. So EAN. So from this, what is cos 30? Root 3 by 2. So when I mention this cos 30 as root 3 by 2, the other side EAB by 2 divided by EAN. I can simplify this. Can you see here? What is EAB equal to? EAB equal to 2 into EAN into cos 30. Substitute cos 30 equal to root 3 by 2. What you get is 2 cancel. EAB is equal to root 3 EAN. Then what you got exactly? EAB is line voltage. I mentioned here line voltage EL equal to, what is EAN? EAN is phase voltage. Therefore is EPH, E phase. So what I got mathematically is line voltage is root 3 times the phase voltage in 3-phase star connection. This is the outcome. Currents are same. The first heading here I began. Currents are same. Voltages are not same. Line voltage is root 3 times the phase voltage. We have just come to the good end of this. It need not be EAB. It can be EBC. I will get the same answer. It may be ECA. I will get the same answer. Therefore, I will get line voltage is equal to root 3 times phase voltage, or phase voltage is line voltage divided by root 3. This is the wonderful relationship in star representation and voltage approach. Then, in case of 3-phase, what is the power total in the system? We have the concept of single phase. In case of single phase, power consumed by a single phase load is given by EI cos phi or VI cos phi. Let me write here. In case of 3-phase power, 3 times power in any one of the phase. If I substitute power in one phase as EPH, IPH cos phi, like a EI cos phi into 3, that should stand as the total power. Yes, it is equal to 3 into. What is phase voltage and line voltage relationship I have here? E phase is EL by root 3. Can you see here? I replaced it. What is IPH and IL relationship? IL equal to IPH. I replace IPH by IL. Then I simplify this. 3 and root 3 cancel. What remains is root 3 EL IL cos phi stand as power in 3-phase AC circuit now onwards. Like a single phase power was EI cos phi, 3-phase power is root 3 EL IL cos phi now onwards. Then what is that phi? Power factor of the particular or power factor angle of the system. So cos of that is power factor. So therefore we learned 3-phase star representation worth 5 to 6 marks question, whichever I have narrated. How to do it? Draw the one diagram which is at the right side here. This only this much, or we can come to this point. Exactly this page with the diagram, with the vector, with the resultant. This carries worth 5 to 6 marks of presentation for your question. So you have to understand. There is a technical stuff of hardly 3 to 4 lines. Rest is a connectivity, how it is being done, that's all. Now I stand at this point. For a 3-phase star connection, line current is same as a phase current and line voltage is root 3 times the phase voltage and power is root 3 EL IL cos phi. This is the standing point of star connection. So in the one of the advantage we saw, it is possible to read two different voltages in three-phase system. So it is what is proved. EAB is voltage between any two lines. EAN is voltage between line and neutral. Therefore, I am able to measure two different voltage. To give a real-time example, in our distribution system, 440 volt three-phase. When I say a voltage, that is the voltage between line 1 and line 2. Line 2 and line 3 or line 3 and line 1. That is called line to line voltage, 440 volt, three phase. Then what is the single phase voltage out of that? 440 volt divided by root 3 I should do. That comes on 239 or 240 volts. What the single phase domestic user gets it. That is the advantage of distribution system being in star fashion. It can provide three-phase power or it can provide single-phase power. Therefore, there comes a relationship. What is that star connection? Similarly, I have delta connection. What is delta connection? I come to the same mechanism. I had a generator having three windings. Windings are such a way connected serially. End of the A to the start of the B. End of the B to the start of the C, end of the C to the start of the particular A. Cyclically, you can see this. It is connected A back to B, B back to C, C back to A. So cyclically, you have connected end to end, and you formed a delta or a triangle-like view. So vertices are brought out like this. So there is no common point generated here. Hence, it is called three-phase, three-wire system. Then you will find a diagram as shown. Three windings are shown, R group, Y group, B group. Then between any one line with the next, if you measure, it is the line voltage. That itself is the phase voltage between any 2 points. So the advantage of delta connection is line voltage is same as phase voltage. Currents are not same. That's what we have to prove here. For that to prove, let us take this diagram visited like this way. I have three windings, winding 1, winding 2, winding 3 connected end to end such that delta is created, leads are brought out for the end connection. You may ask me, you have marked the current going into. What is wrong if I take the current outward? Of course you are right. Whether you are considering a three-phase load or a three-phase generator, the connection and relationship do really exist the same way. So no matter the IA, IB, IC are entering to the A or leaving the A, doesn't make any difference. So therefore, so this is already written in many of the books, you can remember. Let us come to the point. Here I said voltage read between line 1 and line 2, line voltage. That itself is the voltage across this winding. When I go this point, bring this inside, I stand at A. When I bring this point inside, I bring to and stop to B. What is AB? Voltage across this winding. What is between B and C? Voltage across this point. I mean this winding. Therefore, I will find in three-phase delta connection, line voltage is same as the phase voltage, but currents are not same. So therefore, what we will be deriving ourselves? Let IA be the line current, IB be the line current, IC be the line current. Now when you see IA, IB, IC entering the junction A, there is a branching of path. Yes or no? Let us mark A to B, IAB, B to C, IBC, C to A, ICA. Can you see this? IAB, IBC, ICA are the current flowing in the phase winding. Winding 1, winding 2, winding 3. So definitely IA is not same as IB or IA is not equal to ICB, correct or no? Yes, it is not the same. Then what we will be doing? I want to connect. What is the relationship between IA with IAB? So that phase current, line current, I want to connect. For that what I will do? I may pick junction A, junction B, junction C, any one of the junction you pick for your study. Then what I'll be doing? IA is the current entering here, correct? And ICA is the current entering here. What I will do using KCL? IA plus ICA is equal to IAB. I will write it here. So I am able to write a KCL equation. So using that at this A. Similarly, I can do here. What is IB? IB plus IAB equal to IBC. Any one junction I should catch hold to prove the relationship between line current and phase current. Okay, let us move. As we know from the delta interconnection, voltages are same. That's what is done here. Hence, from the study of interconnection of three-phase windings, end-to-end such that a delta is formed, line voltage is same as phase voltage. That is our standing point. Later, applying a Kirchhoff's current law to a junction A, IA plus ICA equal to IAB. Then IA plus ICA equal to IAB. I wrote here, can see IA equal to IAB minus ICA. ICA from this side I took on the RHS side. What it became? IA equal to IAB ICA. Now I want to make a point. What is IA for you? Line current. What is IAB ICA? They are the phase current. You have marked here. Let IAB be the current here. IBC be the current here. ICA be the current here. These are the currents flowing in the phase winding, invariably phase current. Now my question is, when I have a three-phase AC, induced voltages are phase voltages ER, EY, EB, 120 degree apart each other. What about the current flowing in each group, IAB, IBC, ICA? Are they similarly a three-phase waveform having 120 degree difference? Absolutely right. Therefore, current in A group, current in B group, current in C group, namely IAB, IBC, ICA are the three vectors having 120 degree difference between them. That is the logic taken here. Can you see over here? So, ICA, IAB, IBC, these are three vectors of phase current. So, ICA, IAB, IBC, because I want vectorial difference of IAB and ICA. Then it is necessary for me to draw three-phase vectors of IAB, IBC, ICA. Then draw the reverse of this CA. CA has to be put dotted backward. Then take resultant of AB with a reversed vector of CA. What is there here? IAB with a reversed vector ICA resultant of this. So construct this parallelogram of forces like concept. Then get the resultant as IA. It is same whatever we have done here in terms of EAN, EBN, ECN. What we use voltage here, I am using currents here. IAB, IBC, ICA are the three currents I am using here. Then I will be taking a resultant of AB and reversed vector ICA. That led me IA. You can see here. Then make a usual notice. O, A, B, drop a perpendicular from this to the resultant and bisect this. And angle is also bisected. 60 degree total angle became 30 and 30 other side. Whole magnitude of OB now we cut into OC and BC. Now this from this triangle, what is cos 30? Again I will do the same angle here. Cos 30 equal to what? OC by OA. Can you see here? Same principle I use. What is OC? OB by 2. OA as usual. What is OB right now? OB is the resultant. What is that? IA. So IA by 2 divided by OA. OA is IAB. IAB. Now what is IA from this? IA equal to this 2 comes to the denominator into IAB. This side if we transfer it become 2 IAB cos 30. If I apply what is cos 30 over here, root 3 by 2, then if I simplify it, I will be getting IA equal to root 3 IAB. It is the usual derivation what we saw here. This derivation went with the voltage concept. Are you sure? Voltages were there. Line voltage was at the LHS and phase voltage was at the RHS side. Similarly, here I have line current at the LHS side and phase current at the RHS side. And simplify this, you will be getting line current is equal to root 3 times phase current, or phase current is equal to line current divided by root 3. So therefore, now we come to a conclusion. In case of 3-phase delta connection, voltages are same. Phase voltage and line voltages are one and the same, but currents are not the same. Phase current and line currents are having a relation like this way. Line current is equal to root 3 times phase current, or phase current is line current divided by root 3. Then what about the power in 3-phase delta connection? Yes, power in delta connection is again 3 times power in any one of the phase. You can see here 3 into EPH IPH cos phi. Then what is EPH and EL in this delta? Both are same. You can see 3 into EL. What is IPH? IPH is IL divided by root 3, that is written there, and cos phi. If I simplify, it results me root 3 EL IL cos phi. The same equation I had here. I had the same equation, root 3 EL IL cos phi, but magnitude of EL IL are different. Equation is generic, equation is same. 3-phase power is root 3 EL IL cos phi. No doubt whether it is a star connection or delta connection. Definitely voltage and currents are not the same. In case of delta, we find line voltage same as phase voltage. Line current is root 3 times the phase current. Power as root 3 EL IL cos phi. So this is what the measurement we learned. So therefore, how this is useful in our day-to-day life to solve and apply the problems. Let us take one simple problem here. Let me make one knowledgeable effort here. Let's see. What is this example? How the knowledge just now we got useful to us? Let's see. When 3 balanced impedances are connected in star, when the connection star comes to your mind, you should think like this, a Y or star structure. What is it is? 3-phase 415 volt 50 hertz supply. The line current drawn is 20 ampere at a lagging power factor 0.4. Determine the parameters of the impedance in each phase. So this kind of problems will come to us. To solve these, we require knowledge of phase and line voltage relationship, phase and line current relationship, power relationship, power factor relationship, like this way. This is what the one approach. We will come to this problem soon. This is what I wanted to tell you. I know I got relationship. Where do I use them? I have to use them in the real problems like this. Let us take one more problem here. Clear? Can you see here? This kind of problem is posed to us. You are supposed to solve for the requirement. Can you see here? Like this. Correct? So this is how things go. Let us take this problem because this is quite easy for you. It may create interest in you. A balanced Y connected load 8 plus J6 ohm per phase is connected to a 3-phase 400 volt supply. Input supply is 400 3-phase. Load in each branch is 8 plus J6 ohm impedance. Find line current, power factor, active power, apparent power, reactive power, etc. For me it is today Star connection, yes. What is the component available in each arm? Impedance 8 plus J6 ohm. What is the voltage across the total system? 400 volt 3 phase. Therefore, in each path, in each arm like this, what is there? Impedance. What is the impedance of this? R square plus XL square. Same way I have to do here. What is this? R is given, XL is given. R square plus XL square. That's called impedance in each phase. ZPH equal to R square plus XL square or X square. Nothing but 8 square plus 6 square under the root turns you 10 ohm. 10 ohm is in each group. Group 1 arm, group 2nd arm, group 3, like that. Now the question is how to find line current, phase current, power, etc. So we know the relationship between line voltage and phase voltages in star connection. What was the relationship we had here? Just me take you back. This is the application. In case of this, what is the line voltage, phase voltage? Line voltage is root 3 times the phase voltage. What is given to you is 400 volt here. EL is given as a 400. Then what is EPH? 400 divided by root 3. That is EPH. That's what I want to do here. Just to show you an example. Phase voltage is line voltage divided by root 3. 400 divided by root 3 stand as 231 volt. Then using Ohm's law, IPH is VPH divided by ZPH. So, three-phase circuit problems are always solved from per phase representation. It means I should begin from IPH or a ZPH or a VPH. This is the first step we should do. So, once I get impedance, once I get a conversion of voltage, current in each phase possibly is voltage per phase divided by impedance per phase. That is 23.1 ampere. Now, what is IPH? 23.1. In case of star, what is the relationship between line current and phase current? They are equal. Therefore, you got the answer. Find the line current means what? You have to find a phase current first. Then connect it to line current if it is equal or it is other way root 3 into IPH. Like that. So, therefore, IL equal to IPH 23.1. So, we know what is power factor of the system in case of any impedance given to you R and XL. R by Z stand as the power factor. In single phase we have studied this. The same thing R by Z is cos phi 0.8. Then power in three phase is root 3 VL IL cos phi. What is VL given? 400. What is IL? Computed 23.1. What is the power factor? R by Z 0.8. You compute it. This is the power consumed by a star load given to you. That's all. So we will not worry about this. We will see later. If at all you want reactive power, instead of cos, I should use sine. That's all. The cos is replaced as sine means it become reactive power. And total power is remove the cos and sine. Root 3 VL IL. Root 3 VL IL is apparent power. Active power, reactive power, apparent power, like your single phase concept. Only root 3 is extra here. Root 3 VL IL cos phi, root 3 VL IL sin phi, root 3 VL IL. This is the relationship in power rotation. So, this definitely make you something felt. So, yes, this is the real application that we need to use in solving the problem. Similarly, if I take you an impedance in delta, let's the same problem it is. 3 impedances of 4 plus J3 ohm connected in delta across 3 phase 200 volt supply. Now you are configured to think about delta circuit, a triangle like approach. Impedance in each arm is 4 plus J3 ohm. Find the line current, power factor, active power, so-called reactive power, etc. Now the connectivity is delta. Whether it's a star or delta, impedance per phase I have to calculate. That is called ZPH equal to R square plus X square. That stands as 5 ohm. So we know in case of delta, what is the delta relationship? Line voltage is equal to phase voltage. I take you back here. Is it not the relationship we learned just now? In case of delta, line voltage is same as phase voltage. That's what is the advantage taken here directly to solve this problem. So VL, which is given in the problem, is equal to my required voltage per phase. So per phase voltage is line voltage 200. Because I want to calculate per phase current. This is my requirement. To get this, I require Ohm's law relationship. I equal to V by Z. PH, PH, PH. All the elements must be per phase. Okay. So VPH is equal to VL, which is equal to numerically 200. Then impedance of each branch or a path is 4 plus J3, stand impedance as 5 ohm. You may ask me, sir, why you are not writing complex here? Yes, complex if I write, I will be using calculator in complex mode. I will be getting magnitude and angle at the end. Magnitude comes out 40. Angle comes out as a degree of inverse cos 0.8. So I can do it. But it is simpler to work in a conventional computation. Okay. So therefore, complex algebra is not put, even though it is in complex. I am using it simple Z. So therefore, 200 by 5 works as 40 ampere as a phase current. Now in the previous problem here, it was a star connection. Line current was equal to phase current. Is it so here? No. Line current is √3 times phase current. Into √3 I should do. Then only I will be getting line current. So line current is √3 into 40, 69.3 ampere. So this is how the voltages were same here, but currents were not same. Line current was √3 times the phase current I computed. Then as usual, power factor is R by Z. I can do power in the three phases √3 VL IL cos phi. When I substitute √3 into 200 into 69.3 work as 0.8 into 0.8 work as 19.2 kilowatt. So it's very simple. So these are the type of problem we get in three phase. Here what you learned? You learned application of delta relationships. In this problem, you learned application of star relationships. Likewise, I have few more problems. We can see this problem. 3 coils having an impedance of 8 plus J6 ohm connected first in star and in delta across 400 volt 3-phase line. Calculate line current, total power in each case. Is it not a similar work we have done just now? Let us look into this. When coils are connected in star, I know that phase voltage is line voltage divided by √3. Line current is same as phase current. Power is √3 VL IL cos phi. This has to strike to my mind. That's enough. Then impedance per phase is Z equal to root of 8 square plus 6 square, which is equal to 10 ohm. Then voltage per phase in star connection is given voltage line 400 divided by √3, which work as 231 volt. Then I work for current IPH equal to VPH divided by ZPH, which is equal to 231 by 10 as 23.1. No doubt, in star connection, line current is same as phase current, which is equal to 23.1. Then power factor of the circuit representation is R by Z, which is 8 divided by 10, works out as 0.8. Therefore, you are in a position to write what is the total power consumed by a impedance 8 plus J6 ohm per phase in star connection. Such three are there. In one group 8 plus J6, second group 8 plus J6, third group 8 plus J6, connected to what? 400 volt 3 phase. Then power consumed is root 3 VLIL cos phi, sums up 12.8 kilowatt. This is in star. Let us assume in the part 2, what is that? Star and 2, delta. You have to think in your mind. This problem is said to solve considering this impedance is delta connected like a triangle. Each side is having an impedance of what? 8 plus J6, 8 plus J6, 8 plus J6 as a delta. Then we know that in case of delta connection, look at the work here. Phase voltage is same as line voltage. This is the first line should strike to your mind, which is equal to 400. Then immediately the step what I have to do here? Current phase IPH equal to VPH divided by Z, which is 400 divided by 10 equal to 40. Can you relate here? Current here is 23.1, current here is 40. So is it making a difference here? Definitely. Connection wise there is a change, hence the computational values or values computed for the current are different. So we should not copy the answer there from the top to the down. We have to work specifically for the type of connection. When it is a delta, V phase is V line. IPH is by ratio, VPH by Z. Ratio should not give same answer. That's why 400 divided by 10 is 40. Then what about the line current? In case of delta connection, line current is equal to root 3 times phase current. You will see root 3 into 40 becoming 69.28. So you can see here the current is so large by value and voltage is also 400. So therefore, what is the power ability of delta then? You can see root 3 VLIL cos phi equal to root 3 into 400 into 69.28 into cos phi as you did earlier, 8 by 6, 10 equal to 0.8. Get into a numerical data 39.4 kilowatt. Now you will get a statement. Same impedance 8 plus J6 ohm. When I connect in star, it consumes 12.8 kilowatt. When I connect in delta, it consumes 39.4 kilowatt. What is this? What kind of relationship exists between these two? Yes, the outcome of this problem is for a transfer of power from one point to another point in a real power system, delta connection is used. From the generating station to the receiving side, you send a power from a bulk power, it transmitted over a line. So we prefer delta circuit. Only 3 wires are used. R, Y, B, like ABC group, transmit the power via 3 lines. When it comes to a distribution, you require a single phase and 3 phase. You require a 4 wire system. Star we have to use. So therefore I can say delta is having bulk power handling ability 3 times larger than that of star. You can see here 12.8 kilowatt into 3 if you do, it comes 39.4. Therefore, I would say delta circuit is used to or a delta network is used to transfer the bulk power and star network is used to distribute the power. Therefore, this is the kind of interconnection we get by 3-phase interconnections. So we got today in this class or in this problem, star and delta computations are different to each other. Relatively, delta connection is used to transfer the power as it is having huge power handling 3 times larger than that of star connection. So if you find some more problem, I come back to this problem again. Now you are in a very right position to answer this. Now a star connected 3-phase load of 12 ohm and inductive reactance of 16 ohm in each branch. Can you see here? It is connected 12 ohm, 16 ohm in one group. 12 ohm, 16, 12 ohm, 16, like a star connection. A line to line voltage of 415 volt is applied. You can see line to line. Between any two line you measure, it is 415. Just shown only once, but it is R and Y and B and R. Voltage you measure is 415. That is called three phase. So therefore, find line current, phase voltage and power factor. Very simple problem. This diagram will not be given to you. Friends, remember, this circuit will not be given to you. You have to construct the circuit in your mind and you have to draw on a paper. Star connection, it should be like this. And what is there in each arm? 12 ohm resistor and 16 ohm inductive reactance, a coil. You have to make a rough sketch, such three on each. Correct? Then you come to know the given data, 415 volt. Then you have to find out what is required. Now, my friends, get to the point. Find the line current. Line current cannot be done directly. Line current is computed from phase current first and reflected as √3 times of phase current equal to, in case of star, line current and phase currents are one and the same. But in delta, it is different. So what we will be doing? I will start from step by step work. What is VPH? VPH is VL by √3. In case of star connection, phase voltage is line voltage divided by √3. Therefore, it is 415 divided by √3. 239.6 I will get. It is the voltage. You can see here. Line voltage is between any two line. Phase voltage is voltage between any one line and common point. 239.6. So I know the voltage across this path. I know the impedance. Can I not get a ratio of this as a current flowing here? That's what I am doing here. IPH equal to voltage across this, VPH. Impedance of this divided by Z give me phase current. You can see here 239.6 divided by square root of 12 square plus 16 square. That give me a numerical value 11.98. So 11.98 is the current flowing in each phase. It is the same current coming from the line because it's a star connection. In case of star connection, IL equal to IPH. Therefore, IL equal to IPH equal to 11.98. You did the work. The first is complete. Line current is complete. Phase current is complete. And phase voltage, you did already. Phase voltage is line voltage divided by √3, 239.6. Then what is left is power factor. In case of single phase steady VD, what is the power factor? Ratio of resistance to impedance. It is 12 divided by root of 12 square plus 16 square. It becomes 0.6. You did it. It is a worth 6 mark problem. Can you understand this? This very simple approach. Only you have to remember relationships of voltage, current and